Hello everyone. The title of this video is Using Factoring to Find Zeros of Polynomial Functions. Alright, so each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.3 called Graphs of Polynomial Functions, and I'm under the heading Using Factoring to Find Zeros of Polynomial Functions. Alright, and each example I'm doing is either going to be one of the examples from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that are related to this particular objective. Alright, so I have them all written out, so we shouldn't have to go back to the text. And in each of these we're asked to, find the intercepts of the polynomial function. Now, remember intercepts, the y-intercept for a function is very simple to find, right? So remember how to find the y-intercept. That's 0, comma, and then, whatever f of 0 is. It's going to be on the y-axis, so the x-coordinate is 0. So I input 0 to find the so-called, y-intercept or f-intercept. Doesn't matter whatever the output is when the input is 0. Now, part of the title, right, is using factoring to find, what are called the zeros of a polynomial function. Zeros is just another word for x-intercepts. So the x-intercepts of a function are also referred to as the zeros of that function. Well, technically the real zeros are the x-intercepts. We're also going to see in later videos imaginary zeros, which won't show up on the x-axis because the x-axis is a real number line. Another word for zeros that you might come across too are roots. So 3 different words, 3 different things, meaning the same thing pretty much. So if they ask you for the x-intercepts of a function, the zeros of a function, the roots of a function, they're all the same thing. You have, some value in the x-coordinate, comma, and then 0 for the output, right? F of x equals 0. You're basically solving this equation here. When is the output equal to 0? Okay? So pretty easy, I feel. Pretty simple concept. I've gone over how to find intercepts of linear functions in a previous chapter in this particular text. So I'm hoping you've seen that. Alright, so they're just asking us in all these exercises that I'm going to show you, all these examples, find the intercepts of the function. And it's a polynomial function. We are told it's a polynomial function. Alright, so once again, the y-intercept is easy, or I feel the easiest. Just replace the input with 0, right? So what is f of 0? Well, that would just be 0 minus 0 plus 0. So it's 0, right? So the y-intercept, input 0, output 0. Right? The y-intercept is the origin. And I'll put that in a little box. It's one thing we're asked for. Now, do you notice how the output is also 0? So 0 is a 0 of the function. 0 is an x-intercept, the point 0, 0. Well, we'll get to that. Alright, so now for the x-intercepts. So I'm going to replace f of x with 0. Right, replace the output with 0. Right, we have 0 equals x to the fourth minus 19x squared plus 30x. Right? And we're going to solve this by factoring. Right? The title is using factoring to find zeros. And you may recall from the solving of quadratic equations in previous videos, the way we solve the quadratic equations by factoring is exactly the same way we're solving these equations by factoring. You have 0 on one side, everything else on the other, and then you factor that polynomial completely. Well, if I look at these three terms, they all have a common factor of x, right? So I factor x out. And then we'd be left with x cubed minus 19x and then plus 30. Okay. Now this here, x cubed minus 19x plus 30, this can be factored further, but we haven't seen a method for that yet. Alright, we haven't seen a method for that just yet. So what I'm going to do is I'm going to factor completely. Well, I'll just say factor because again, this can be factored over the integers, just not with the method we've seen. So what we're going to do, if we get down to cubics, degree 3 or higher that we can be factored, we're going to use some technology here, right? But not by a method we know yet. And don't worry, we'll get to that method, but not by a method we've seen previously. We're gonna get to a method to help me solve this, and in fact, knowing that x equals 2 makes this 0 will actually lead you to a way to factor this. All right, but for right now, just going to kind of leave it and say, oh, remember that zero product property. If a product equals 0, then one of the factors has to be 0. So either x equals 0 or x cubed minus 19x plus 30 equals 0. And we already saw this, right? So 0, 0 is an x-intercept. We saw that earlier. It would say that x equals 0 is a 0, right? Is a 0, one of the zeros of this polynomial function. And from this, I'll tell you right now that x equals 2 works, right? Because 2 cubed is 8. 19 times 2 is 38. 8 minus 38 is negative 30, plus 30 would be 0. So 2, 0, right? That's another x-intercept. Or you could say that x equals 2 is another 0 of this function. But let's go to the calculator. Alright, now there's a free online graphing calculator I've been showing you in these videos at a website called desmos.com. So I'm going to do is I'm going to enter the polynomial function they gave us, f of x equals x to the fourth minus 19x squared and then plus 30x, and we'll see the intercepts here. In fact, not only does 2 work, but so does 3 and negative 5. All right, we already saw 0 working, right? But 2, 3, and negative 5 also work, and we can check this, right? Going back to my paper here. Not only does x equal 2 make that true, but so does x equals 3, right? 3 cubed is 27. 3 times 19 is 57. 27 minus 57 is negative 30, plus 30 is 0. Right? So there's another 0 of the function, another root. So 3, 0. And then we saw also from the graph that x equals negative 5 is another 0. right? Another x-intercept, and we can double check it. You know, negative 5 to the third power would be negative 125. And then negative 19 times negative 5 would be positive 95. And then, you know, negative 125 plus 95 is negative 30, plus 30 is 0. So all these work, right? 2, 3, and negative 5. And again, these numbers, 0, 2, 3, negative 5, you know, where the x-intercepts are, again, they're also called the zeros of the function or the roots of the function. Right? Just keep that in mind that you might see those words. Yeah. So this one was a little tricky, maybe I picked this one on purpose because it had that trickiness to it. You know, you can factor it a little bit, and like I said, later on in the course, later on in the book, we'll see a method for factoring this cubic polynomial, right? Because unfortunately we can't really factor this with any method we've seen so far. Right. Alright. So, yeah, so we may have to use some technology, right? But that's not a problem. Right? We should be able to see the intercepts, see the zeros, see the roots from a graph also. Okay. Next example. Now the next one's pretty nice because the polynomial is already totally factored. Right, we have a c of t, right? So now the horizontal axis is the t-axis instead of x, right? And you could still call the vertical axis, you know, the y-axis if you want, but you could also call it the c-axis. You know, the name of the values of c here, c of t. All right, so again, this is already completely factored, right? You can't break down t minus 4 and t plus 1 and t minus 6 any further. So it's already factored. So it should be pretty easy now to state all the intercepts. Now the y-intercept, I'll just put y int. You're just plugging in 0 for t here. Right? What's c of 0? So that'd be 2 times negative 4, right? 0 minus 4, times 1, 0 plus 1, times negative 6, which is 0 minus 6. Multiplying all these, negative 8 again, and then times negative 6 would be positive 48. Right, so this has the point 0, 48 on the graph, right, which is not on the horizontal axis, right, so it's not one of the zeros. It's one of the, it's the y-intercept. And now for the t-intercepts, and just replacing c of t with 0, replacing the output with 0. So 0 equals 2 times t minus 4 times t plus 1 times t minus 6. And I'm hoping it's obvious, right? You can apply that zero product property to say that, well, one of these factors has to be 0 then. Obviously 2 can't be 0, but either t minus 4 equals 0, or the factor of t plus 1 is 0, or the factor of t minus 6 is 0. And here we get our zeros. T equals 4, negative 1, and positive 6. Right? And here are what are called the zeros of this function, or the roots. Right? Zeros / roots. So on the t-axis here, you got 4, 6. There's point there, and then negative 1 point there. Right? Negative 1 comma 0, 4 comma 0, 6 comma 0. And then you could even go further and talk about the end behavior. Right, this would be a degree 3 with a positive Lie coefficient, so it's going to start off down here, go through that, and then go through that, come back down, come back up, and got an end going up like that. It's going to look something like this. All right, that's a very, very rough sketch, but just to verify that all these intercepts are correct, I'm going to go back to that Desmos site and enter this polynomial function and see what we get. C of t equals 2 times the quantity t minus 4 times the quantity t plus 1 times the quantity t minus 6. And yeah, you see this if I zoom out. It looks kind of like what I drew on paper. Just very, very rough. You got negative 1, 0, right? 4, 0, 6, 0, right? All those zeros, all those roots, the t-intercepts that I mentioned on paper. And if you want to go to the y-intercept, right, that was at right here 0, 48, as we also mentioned. Okay. All right. So next example, and it's all the same. All these are the same. All right, and we'll go to the technology to verify each time. All right, so this one's another function of t, right? C of t equals, and again, this is in factored form. So identifying the zeros, identifying the roots, the t-intercepts should be pretty easy. All right. So I'll just make a rough sketch off to the side here. Right. So again, the y-intercept, right, the intercept on the vertical axis, just plug in 0 for the input. Well, since there's a factor of t, this is just going to be 0. All right, so you got the origin 0, 0 is the vertical axis intercept, right, the y-intercept. So that means that 0 is also a t-intercept, right, it is also a root. So find the zeros, right, the t-intercepts. Well, t equals 0 is one of them. That makes this factor 0. T equals 2, right, this factor t minus 2, that will make that 0. So you'll have 2, 0 on it as well. And t equals negative 1. Again, I'm hoping it's obvious after that first example. Alright, and then this is going to be a degree 1, 2, 3, 4. I'm counting this one twice, because there are two of them. Is t minus 2 squared. So it's degree 4 with a positive lead coefficient. It's going to go up on the end, on both ends, right? To positive infinity on both ends. It's going to come down, have to cross at negative 1, have to come back, cross at 0, and then come back again. And then what you're going to see is, since t minus 2 has a square on it, it's going to act like a square polynomial. It's going to bounce off the horizontal axis at 2 and then come back up like this, something like that. And in the next video, we'll talk about more about the behavior of a graph near these zeros. But for right now, just know that if you have an even power on your factor, the graph's going to touch the axis and then bounce back. And if you have an odd power, it's going to cross over. But again, that'll be talked about in more detail in the next video. All right, and so here we go. All right, there's the zeros. Let's take a look. Again, I'm going to go back to that Desmos site. We had c of t equals 4 times t minus 2 squared times t plus 1. And again, my drawing wasn't great, but it had the same kind of shape as this. Started off going up to the left, down, and then bounced, crossed at negative 1. All right, see negative 1, 0, then turned at some point, and then crossed at 0, 0, turned at some other point, then hit 2, 0, and then came right back, and then went to infinity on the far right. All right. Great. All right, next example. All right, so the next one's not factored. All right, examples 2 and 3, the polynomials were factored already. So let's factor this one. So again, it's a function of t instead of x. If you want to change things to x, you can change the input variable to x. There's nothing wrong with that. Now let's factor this thing. Right? Now all the terms have a common factor of 2t squared. Right? That would be the greatest common factor. So I pull out 2t squared, and then the factor remaining would be t squared minus 4t plus 3. But it's not factored completely, right? Because this t squared minus 4t plus 3 can be factored even further. So 2 times t squared, and then t squared minus 4t plus 3 factors to t minus 3 times t minus 1. Alright, now again the intercepts. The y-intercept is easy. When I plug in 0 for t, the output's 0. Right? Every single term would be 0. And then that's also a horizontal t-intercept, right? So t equals 0 is a 0. And then 3 and 1. Right? If t were 3, the output would be 0. And if t were 1, the output would be 0. So you could say these are the intercepts. And, the zeros or the roots are t equals 0, t equals 1, t equals 3, right? Those are the zeros of the polynomial. And once again, a very rough sketch can be made. 0, 0, 3, 0, 1, 0. And, even degree, positively, coefficients, got to start going, it's going up on both ends, right? You can talk about the end behavior. Then it's got to come down as you go left to right. It's going to touch the horizontal axis at 0 here, but because t squared, that's where the factor that's made 0 by t equals 0 has an even power on it. So it's going to come right back. It's not going to cross over, and then it's got to come back down. It's got to turn somewhere and come back down to 1, 0. Now t minus 1 only has a power of 1 on it, an odd power, so it's going to cross over. It's got to turn at some point and then come back to 3, and again t minus 3 only has an odd power on it. It's going to cross through and then end going up to the right forever as it should. And it's going to look something like this, maybe a little thinner. I don't know exactly where these turning points are, right? I'm not finding those. That's going to be more for a calculus class when you get into that, but you can at least have a rough idea as to how the function's moving as you go from left to right, if you know where all the intercepts are and what the end behavior is. Let's take a look. Alright, so again, I'm going to enter this on my Desmos site here. So we have c of t was 2t to the 4th minus 8t to the 3rd plus 6t squared. Alright, and it looks similar to what I wrote, right? C0, 0, C1, 0, C3, 0. Right. And it's going up to the far left and up to the far right, right? The end behavior is correct as well. And you see how it touches at 0 but doesn't cross, and then it crosses at 1, it crosses the axis at 3. And I talked about that a little bit too, but again, that's going to be the next video talking about what happens near these zeros, near these intercepts. Okay. Next example. I'm doing the same thing every time here. Alright, now you just got 2 per page, because hopefully after watching the first 4 you get the idea. So f of x equals x to the 4th minus x squared. That factors pretty easily. Alright, pull x squared out, and then you'd have x squared minus 1. But even that factors further. Alright, that's a difference of squares. That would factor to x minus 1 times x plus 1. So the intercepts would be at 0, 0. Right, clearly when x equals 0, the whole thing would be 0. When x equals 1, the whole thing would be 0, the output. And when x equals negative 1. Right. So x, y, you got 0, 0, you got 1, 0, you got negative 1, 0. Again, it's an even degree, positively coefficient, so it's got to be doing this. And it comes down, crosses at negative 1, because x plus 1 has a power of an odd power. Turns somewhere. Then it's going to hit at 0 and turn back, because x has a even power. And then it's got to turn somewhere and then cross at 1, right? So that we get the end behavior we want. And it's crossing at 1, again, because x minus 1 has an odd power. Right? Odd powers, it's going to cross. Even powers, it's going to bounce. Right? It's going to hit the axis and come right back. All right, and let's take a look. Let's verify this. So we have f of x equals x to the 4th, x raised to the 4th, minus x squared. And you see the intercepts, right? Negative 1, 0, 0, 0, 1, 0, and you see how it's crossing at negative 1, crossing at 1, but bouncing off the axis, right? Just touching the axis and bouncing back at 0. Okay. Next example, right? Again, finding these intercepts should be simple. Again, if you know how to factor, and if some things can't be factored, if you don't know how, go to the calculator and check it out. See if you can find the intercepts there, the zeros, the roots. All right, so once again, we have a nice polynomial function written in standard form here, general form, highest power to lowest power. Greatest common factor would be x. We have x squared plus 6x minus 7 left over. But that quadratic, right, you should know how to factor quadratics if they can be factored. That factors even further. That would factor to x plus 7 times x minus 1. Alright, so the intercepts, one is at 0, 0 again, clearly if x equals 0, the output would be 0. Another one's at negative 7, right? And another one's at positive 1. And each one of these has an odd power on it, right? These are all to the first power. So the graph is going to cross the axes at all these at 0, 0, and here's negative 7, 0, and 1, 0. And it's got an odd degree, positively coefficient, so it's going to go down to the left, up to the right, the end behavior. And it's going to cross at negative 7, turn somewhere, cross at 0, turn somewhere, and then cross at 1. Right? So something like this. And let's just verify that our intercepts are correct, right? You should be checking solutions all the time. This function was f of x equals x cubed plus 6x squared and then minus 7x. Right? And you see the negative 7, 0, 0, 0, 1, 0. The graph crosses the axis at all these, as we said it would, and this down to the left, up to the right for the end behavior. Looks pretty similar to what I had drawn. Okay, moving on. Alright, this next one is something that you can factor by grouping. Remember, if a cubic polynomial has 4 terms, you might want to try factoring it by grouping, which was, put in parentheses the first 2 terms, plus, and then in another set of parentheses the next 2 terms. You factor each group. First group has a common factor of x squared. That'd be x squared times the quantity x plus 2. The second group has a common factor of 9, but because the lead is negative in this group, I'll pull out negative 9. I'll just turn the plus into a minus 9. And if I pull out negative 9, you'll have x plus 2 left. And then look at the whole thing, right? Both these products left over have this factor of x plus 2 in common, so that comes out. And then you're left with the other factor of x squared minus 9, which can be factored even further, right? This is a difference of squares, x squared minus 3 squared. So that's x plus 2 times x minus 3 times x plus 3. And now again, I hope it's obvious what the intercepts are. You'd have 0, 18, or negative 18. Right? If x were 0, all the first 3 terms up here would disappear. You'd be left with an output of negative 18. So that's the y-intercept. So there's not a 0 or a root there. Right? That's not an x-intercept. The x-intercepts would be at negative 2, 0, 3, 0, and negative 3, 0, right, looking at the factors. And again, all these factors have the first power on them, have an odd power. So the graph will just cross over at these intercepts. Right? So negative 2, 0, negative 3, 0, and 3, 0. And you have, 0, negative 18 as the y-intercept. And it's an odd degree positively coefficient, so it's going to be going down to the left, up to the right with the end behavior. And it's going down, crossing at negative 3, turning at some point, crossing at negative 2, turning at some point, and then crossing at 3. And again, it's got to go through I don't know. I really don't know if 0, negative 18 is a turning point. I don't think it would be. yeah, I don't think it would be. I think the turning point would be somewhere else. I'm just drawing a very, very rough sketch here. But as long as you know the end behavior and how the graph acts, at the intercepts, you'll be able to make a decent rough sketch. But yeah, so here's all the intercepts, right? That's what they asked us for, the intercepts. And let's just verify these once again. So the function this time was x cubed plus 2x squared minus 9x minus 18. All right, and you're seeing, see, negative 3, 0, negative 2, 0, and 3, 0, and 0, negative 18. Right, yeah, you see it's not the turning point, so my drawing's a little off, but turning point's over here, down here somewhere. But the y-intercept is correct, right? And the end behavior is right, down to the left, up to the right. The end behavior is correct, the intercepts are correct. So my rough sketch isn't terrible. It's just the turning points are a little off. Okay. Then example 8. Same stuff. Now, this is a degree 6 polynomial, but you may recall from, again, previous videos, it's been a while, but factoring. This is like a quadratic. See the power on the first term is 6, which is twice the power on the middle term. Right? And then you have a constant. So this is like a quadratic, or they would call it quadratic in form. And that means you can factor it just like a quadratic, but remember that it ends up being a 6-degree polynomial. So this actually factors to x cubed minus 8 times x cubed plus 1. Instead, because if this were x squared minus 7x minus 8, it would factor to x minus 8 times x plus 1, but instead of x, you have x cubed. Right? I want a degree 6 polynomial. All right, and then these are actually more factorable. Remember, this is a difference of cubes. This would factor to x minus 2 times x squared plus 2x plus 4. All right, that's that. And then this is a sum of cubes, which would factor to x plus 1 times x squared minus x plus 1. And then these two here, these two quadratics are not factorable. In fact, they have imaginary zeros, or they have complex zeros with an imaginary part. You can try, finding what makes these 0, and you'll see there will be an imaginary in it. All right, so not going to worry about those for the intercepts. Only the x minus 2 and x plus 1 are all that matter here. So my intercepts are 0, negative 8, right? Because if x were 0, the output would be negative 8. There's the y-intercept. And then for the zeros, right, the x-intercepts, the roots would be at 2, 0, and negative 1, 0. And that's it. Again, like I said, these two quadratic factors have zeros that'll have an imaginary part, so they're not going to be on the x-axis, right? The x-axis is real numbers only. So here's 2, 0, negative 1, 0. You got 0, negative 8, right? Y-intercept. It's an even degree positive lead coefficient, so it's going to be going up to the left, up to the right, for end behavior. And the graph's going to cross at negative 1, come down, hit this, and it's going to turn at some point and then cross at 2. I don't know exactly how, but should be crossing at these because they have odd powers on their factors. And once again, let me just verify that these intercepts and end behavior are all correct on Desmos. So here's f of x equals x to the 6th minus 7x to the 3rd minus 8. Yeah, and you see the negative 1, 0, 2, 0, and those are the only intercepts. Yeah, and there's some weird stuff happening down here. Alright, but I didn't ask about that. 0, negative 8, right? The y-intercept, like I said. Up on left, up on the right, the end behavior is correct, right? You're not going to be able to find, based on what we know right now, you're not going to be able to find these weird turning points. Okay? That's going to be something for a calculus course later, Calculus 1. For right now, again, all we're worried about is what's the end behavior, what are the x-intercepts or the zeros or the roots, and what's the y-intercept. Right? That's all I really want to know right now. Alright, and then I've got just one final page where I'm doing the same stuff. Alright, same stuff. Alright, so on number 9, example 9, again I have something that I can factor by grouping. First two terms I'd pull out x squared, and you'd have times x minus 3. Second two terms I'd pull out a negative 1, because the first term there, the lead is a negative, times x minus 3 again. And then these two have x minus 3 in common. Now when I remove x minus 3, what would be left would be x squared minus 1, which is a difference of squares. That would factor to x minus 1 times x plus 1. And there we go. Now the intercepts, the y-intercept would be 0, 3. And then you have 3 x-intercepts, 1 at 3, 0, 1, 0, and negative 1, 0. And there's all the intercepts. And if you want to make a very rough sketch, but again, I'm going to go to the calculator, look at a better picture. We got 0, 3 for the y-intercept, and then 1, 0, negative 1, 0, 3, 0 for the x-intercepts. It's a positive lead coefficient, odd degree, so that's going to be going down to the left and up to the right for the end behavior. And because all these factors have even odd powers, they're all to the first power, the graph's going to cross the x-axis at all these intercepts. Cross. Again, I don't think the turning point's there. And then it's going to cross and do something like that. Again, it should be smoother than what I've drawn. Let's see an actually good picture of it on the Desmos site. So we have x to the third minus 3x squared minus x plus 3, and there you go. No, it's not a turning point. See, 0, 3 is not the turning point. It's actually at that point there. But 0, 3 is the y-intercept. You got negative 1, 0, 1, 0, and 3, 0 is the x-intercepts, and you see the graph crossing the axes there. And down to the left, up to the right, the end behavior is correct as well. Good. Alright, and then one final example where I'm doing, again, the exact same stuff. I'm going to factor the polynomial completely, state all the intercepts, and I'll make a rough sketch myself, and then we'll look at the Desmos site. These have a common factor of x squared, and if I pull out x squared, you then have x to the fourth minus 3x squared minus 4. And then this degree 4 polynomial here is like a quadratic. It's kind of like example 8 with the 6th degree. You see how the first term has a power of 4, which is double the second term, and then you have a constant. Anytime the 3 terms, the first term has a power that's double the second term, and then you have a constant, it's exactly like a quadratic. So this should be factored further. This can be factored actually to x squared minus 4 times x squared plus 1. And x squared minus 4 is a difference of squares. That factors to x minus 2 times x plus 2. And then x squared plus 1 is a sum of squares. You can't factor a sum of squares over the integers anymore. So here we go. That's as far factored as this is going to get. And the intercepts are clearly 0, 0. Right? If x were 0, the output would be 0. So there's an x-intercept and y-intercept. 2, 0, negative 2, 0. And then this last factor, right, the x squared plus 1, this would have imaginary zeros, right? I squared plus 1, negative I squared plus 1. Those would be 0. I and negative I. But those aren't going to show up on the x-axis, right? So here are the only x-intercepts we care about. Right? And we'll get into later videos actually caring about the imaginary ones, but for right now, we only care about what's going to actually show up on the x-axis. What are the real zeros? The 0, 0, 2, 0, negative 2, 0. It's got even degree, positive lead coefficient, so it should be going up on both ends, up to infinity. And the x minus 2 and x plus 2 have odd powers, but the x has an even power. So at x equals 0, the graph's going to hit and bounce back. So it'll cross at -2, turn some point, hit at 0, and then bounce back, and then turn again, and then cross at 2. And again, that's terrible. My paper shook on me. It looks something like that. And once again, last time, here we'll go to the Desmos site. I will enter this function, and we'll see that the end behavior and intercepts match up. So it was x to the, oops, no, it was x to the 6th, wasn't it? X to the 6th minus 3x to the 4th minus 4x squared. And yeah, you see that. -2, 0, 0, 0, and 2, 0. And you see how it's crossing the axis at -2, crossing the axis at 2, and bouncing off the axis at 0. And up on the left, up on the right. You know, the end behavior matched. Okay. Great. Alright, so that was a lot there. I mean, I was doing the same thing every time, so I'm hoping that, you know, watching me go through these 10 examples here helps you in some way, you know, when you're asked to use factoring and, you know, maybe some technology like Desmos or whatever graphing calculator you have to identify the y-intercepts and also the zeros, right, or the roots or the x-intercepts of a polynomial function. And thank you very much for watching.